Environmental Systems and Societies for the IB Diploma Program, Pearson book, 3rd edition. We are in the water chapter, section 4.3. We're starting with the introduction to 4.3, and then we'll continue with 4.3.1. Right? So 4.3, aquatic food production systems. Right? Big systems for producing food for humans and our livestock probably as well from water sources. So aquatic means water. Guiding questions. How are our diets impacted by our values and perspectives? So how do we see the world? What do we care about? And how does that affect what we eat? To what extent are aquatic food systems sustainable? Okay, our methods for feeding ourselves from water-based systems, lakes and rivers and seas, oceans, how sustainable are these methods, these aquatic food systems? 4.3.1, phytoplankton and macrophytes. What great words, phytoplankton and macrophytes. Let's start with phytoplankton. Phytoplankton are autotrophs. That means self-feeding. Remember the word troph, like in eutrophic and trophic levels. Trophic means just has to do with food or feeding, right? So phytoplankton are autotrophs. That means they are self-feeding. They obtain their energy through photosynthesis, using light from the sun. They are found in the well-lit surface layers, the euphotic zone, or the well-lit surface layers of oceans and lakes. Okay, so these are little organisms that live in water where the sun can reach, so not so low down that it's too dark. They live in the surface water, and they're not really plants, but they're kind of plant-like, okay? And they're called phytoplankton. Phytoplankton form the base of marine and freshwater food webs. The way plants are kind of the base of terrestrial food webs. That means land-based food webs, aquatic food webs. So here it says marine and freshwater food webs. You could also say aquatic food webs. So phytoplankton are the producers. Phytoplankton are producers and create organic, meaning carbon, compounds from dissolved carbon dioxide in the water. Although plankton only account for about 1% of global plant biomass, okay, so here they're considering phytoplankton to be plants. So they're about 1% of the world's plant biomass. They account for about half of global photosynthesis activity and are responsible for at least half of the world's oxygen production. That's really important. Phytoplankton produce 50% of the world's oxygen. Important little critters, little planty dudes, right? They are also a vital component of the Earth's carbon cycle. Some plankton are heterotrophs and feed on other plankton or detritus. These are consumers and are known as zooplankton. Zoo kind of just means animal, the way phyto kind of means plant. Okay, so some plankton, which are also itty bitty little dudes that live in the water, they eat other plankton, or they eat detritus. So they have to eat something. They don't do the photosynthesis thing. So you have phytoplankton that do photosynthesis, and you have zooplankton, which eat stuff. Okay. During photosynthesis, phytoplankton assimilate CO2, carbon dioxide, and release oxygen, just like terrestrial plants. Take in the carbon dioxide and release oxygen. If solar radiation is too high, Phytoplankton may be photodegraded. It means that radiation, solar radiation, can break them apart. Bacteria can also degrade them. Okay, so degrade kind of just means break down or break apart. So bacteria can also do that to them. Phytoplankton cells depend on nutrients for growth, including macronutrients such as nitrate, phosphate, and silicic acid. I'm going to go with that as the pronunciation, silicic. These nutrients are common where ocean water is upwelling. Remember, we've talked about upwelling. We talked about when the air blows the surface water away, you got that cold, deep, nutrient-rich water that comes up to replace it. That's upwelling. And we talked about it's nutrient-rich, but what does that mean? Well, these nutrients such as nitrate, phosphate, and silicic acid. Okay. In contrast, in large areas of the oceans, such as the Southern Ocean, phytoplankton are limited by the lack of the micronutrient iron. So in some places there isn't so much phytoplankton because there's not enough iron. Phytoplankton also depend on B vitamins for survival. Thus, oceanic areas lacking in B vitamins contain limited phytoplankton populations. Okay, so the phytoplankton, they need the right amount of sun, not too much sun, or they fall apart. They need the right amount of iron, not enough iron in the water. They can't survive there. Not enough B vitamins, can't survive there either. So figure 4.49, I'll put that up for you, shows the factors that affect phytoplankton productivity. Each of these factors is expected to be affected by global changes, such as oceanic temperature increase, the warming of the oceans, changes in ocean stratification and circulation. Talked about ocean stratification in the previous section. Okay, that's when you've got the layers in the water separated by temperature because cold water sinks, right? Cold, more saline water sinks. So these changes in ocean stratification and circulation, where the water is moving, those big ocean circulation charts, remember those? And changes in cloud cover and sea ice, resulting in an increased light supply to the ocean. Remember, if they get too much light, they can degrade. And if you've got not enough cloud cover, then you've got too much light. If you don't have enough ice covering it, you've got too much light. Right? So you've got increased light supply to the ocean surface. Ocean acidification, talked about that too. Too much carbon dioxide in the water causes ocean acidification. Ocean acidification and warming will also reduce nutrient supply due to increased stratification of the water column. All right, we talked about that. Ocean acidification can mean that you don't have that mixing anymore, so those nutrients that are down in the bottom don't come up, the B vitamins and the iron that the phytoplankton need. Due to increased stratification of water column and reduced mixing of nutrients from the deep water to the surface. I'll say that one more time. Ocean acidification and warming will also reduce nutrient supply due to increased stratification of the water column and reduced mixing of nutrients from deep water to the surface. Phytoplankton has a significant impact on atmospheric gas composition. So the gases that are in our atmosphere are affected by phytoplankton, these little dudes that live in the ocean and big lakes. Inorganic nutrients and trace element transfers, as well as the transfer and cycling of organic matter via biological processes. Wow. Okay, so phytoplankton affect a lot of things on the global scale. Fixed carbon is rapidly recycled and reused in the surface ocean, while some biomass sinks to the deep ocean where it is remineralized. Okay, let's read this little pink section here about ocean acidification. Ocean acidification can have a negative impact on phytoplankton growth, particularly on coccolithophore. I'm guessing that's how that's said. Coccolithophore phytoplankton. These have a calcium carbonate shell, and remember calcium carbonate shells? What happens with acidification? Okay. That shell, called a cocosphere, is vulnerable to ocean acidification. However, due to their short lifespans or generation times, some phytoplankton may adapt to changes in pH over a short time scale, months to years. In oligotrophic oceanic regions, oligotrophic means nutrient poor. Oligotrophic doesn't have enough nutrients. Such as the Sargasso Sea, phytoplankton are characterized by small-sized cells called nanoplankton and picoplankton, also referred to as picoflagellates and nanoflagellates. Within more productive or eutrophic ecosystems, such as those with upwelling currents or high terrestrial inputs, so nutrients coming from land, larger dinoflagellates, it's probably flagellates, are more frequent and form a larger portion of the biomass. Okay. So going back to the main text and look at the little subheading, aquaculture. Phytoplankton are a vital food supply in aquaculture and mariculture, marine farming. So aquaculture is basically all water-based farming, like we're growing things in water as opposed to on land. And mariculture is specifically to marine systems, salty systems. Both use phytoplankton as food for the animals being farmed. In mariculture, phytoplankton are naturally occurring, whereas in aquaculture, phytoplankton must be obtained and introduced directly. Okay, so when you've got aquaculture like in tanks, inside somewhere, or even outdoor tanks, the phytoplankton isn't just naturally there, you've got to put it in. The phytoplankton can either be collected from a body of water or cultured. That means grown. Macrophytes. Aquatic plants, those are macrophytes, aquatic plants, are those adapted to living in aquatic, freshwater and saltwater environments. So phytoplankton are like microscopic. They're teeny tiny, right? Whereas macrophytes, they're bigger. Okay? Macrophytes grow in or near the water and can be emergent, submergent, or floating. Macrophytes are producers, because they're plants and they do photosynthesis, and therefore form the basis of the food chain for many organisms. They also slow down water velocity in rivers, increase sedimentation, and may capture pollutants. By capture, it usually means in their roots. Like if there's pollution in the bottom of the riverbed, they might pull that up into their leaves so that the pollution isn't in the soil anymore or floating around in the water. It's inside the plant. Okay, so they can capture pollution, maybe. But they slow down the river velocity because if you've got a current, you've got all these plants growing there, all these reeds, things like that. Well, obviously it's going to slow things down. And when you slow down the current, the sediment, the soil particles that are in the water can fall down. And that's sedimentation. Fall down to the ground. To survive within the water, either submerged or at the surface, plants have many adaptations, including floating leaves, dissected leaves, and or lightweight cells. The main factors affecting the abundance and distribution of aquatic plants is the availability of water, nutrient availability, disturbance by waves, salinity, and grazing. Submerged plants have less access to carbon dioxide and light than terrestrial plants in general. Fully submerged plants, that means totally underwater, like kelp, have no requirement for woody biomass. So they don't grow woody biomass. Many submerged plants have finely dissected leaves to increase surface area for the exchange of minerals and gases and to reduce the impact of water flow in rivers. Some floating plants have developed leaves that have stomata on the top surface of the leaf in order to capture atmospheric CO2. So usually the stomata is on the underside, but not in these floating plants. Emergent plants grow in water but are partially exposed to air. Leaves can photosynthesize more efficiently in air, but the main reason for having part of the plant on the water surface is reproduction. For example, the flower may be on the surface in species of reeds and flowering rushes. These are kind of these wide, hollow grass things that grow in the water. Well, most of the a lot of the plant is submerged, but they have a part that is above water for reproductive reasons. Submerged macrophytes grow underwater and may or may not have roots attached to sediments at the water's base. Helophytes are partly submerged plants, such as reeds and yellow flag, that grow in marshes from submerged buds. Floating leaved macrophytes, such as water lilies, see in the picture, and pond weeds have root systems attached to the riverbed or lake bed and leaves that float on the water's surface. Some macrophytes, such as wild rice, watercress, and Chinese water chestnut, are important food crops. They are things that we eat. Macrophytes can be important for wastewater treatment, especially in small-scale sewage works. A decline in macrophytes may suggest declining water quality caused by salination, salt coming in, and or large-scale use of biocides. That means chemicals used to stop algae from growing on boats or to kill weeds in your garden, and then the water runs off and goes down into the streams and then into the lakes. Those kinds of biocides. Pesticides are also biocides. Some macrophytes have been introduced into new environments and can become locally dominant in many temperate areas. For example, water hyacinth in South Africa and New Zealand stone crop. Okay, so there can be macrophytes can be invasive. 4.3.2 Human consumption of fresh water and marine organisms. So consumption, that means eating or using in some way, like for tools or clothing or toys, whatever. Fauna, that means animals. Humans consume organisms from freshwater and marine environments. Of course we do. According to the State of the World's Fisheries and Aquaculture, in 2020, finfish represented about 85% of total marine capture production. So fish that had fins were 85% of what we were fishing in marine systems. With anchoveta, the top species harvested. However, only a small number of staple species dominate aquaculture production, particularly grass carp for global inland aquaculture, so inside far from the coasts, and Atlantic salmon for marine aquaculture. We can look at 4.51, the share of main groups of species in exports and aquatic products by value from 2020. Okay, so you got this dark blue part of the inner ring. It says finfish, 67%, and then that's kind of divided in the outer ring. So to other finfish, salmon, trout, and smelt, tuna, bonito, and billfish, cod, I don't know what that is, hake, haki, haddock, and other pelagics. So it's kind of divided up there. And then you've got crustaceans and how that can be divided up. So we have a pretty good idea of what we're fishing and to what extent. That's kind of neat that we have that data, isn't it? In 2020, global exports of tuna, bonitos, and billfish accounted for almost 10% of the value of exports of aquatic products that were worth over 14 billion US dollars. So that's looking at this picture. Okay, I can put the picture up there. It's figure 4.52. This proportion has remained relatively steady for many decades, reflecting tuna's popularity with people worldwide. We eat a lot of tuna. We like tuna. The trade in tuna can be divided into two main categories: processed and preserved tuna, tuna in a can, and high-quality fresh tuna for the sushi and sashimi market. Bluefin and big-eye tuna are generally used for sushi and sashimi. Skipjack, yellowfin, and albacore tuna are used for processed products, which can be frozen and transported around the world. Thailand has a large tuna processing industry, which supplies the USA, while Ecuador supplies much of the tuna destined for the European Union. Okay, so Europe gets its tuna from Ecuador, and the US gets its tuna from Thailand. There are also smaller processing industries in Asia, Latin America, and Africa, illustrating how important the tuna trade is globally. Flora, that means plants. Seaweed has many uses, including as a food, as a flavoring, for thickening soups and broths, as an herbal tea, as a medication for sore throats, for use in baths to cleanse skin, and as a soil fertilizer. The pepper dulce seaweed has been described as the smallest and most beautiful of all the Irish seaweeds. It can be found in rock pools or on the base of rocks when the tide is out. It is also known as the truffle of the sea. Truffle is a kind of mushroom. Truffle of the sea, due to its sweet, savory taste. Due to its size, it is generally used as a garnish, as a decoration, with mussels, clams, and scallops. It has a shelf life of just 2 days once harvested. That means you can have it looks nice and fresh for 2 days and then it goes bad. So it tends to form part of local dishes in coastal areas. It can be dried and powdered, although the flavor of the dried version is not as strong as the fresh pepper dulce. 4.3.3 Increasing demand for freshwater and marine organisms. We want more. We want to eat more of them. Demand for foods from freshwater and marine environments is increasing due to the growth in human population, more mouths to feed, and changes in dietary preferences. We like fish more compared to before. According to the Food and Agricultural Organization, FAO, Food and Agricultural Organization, global fisheries, that means places that raise fish, and aquaculture production reached a record 214 million tons in 2020. This consisted of 178 million tons of aquatic animals and 36 million tons of algae. We also grow algae, and you eat that. Different things. This was largely due to the growth of aquaculture, particularly in Asia. The amount destined for human consumption, excluding algae, so we're going to just put that on the side here, was 20.2 kilograms per capita, so per person, more than double the average of 9.9 kilograms per capita in the 1960s. So per person, we eat a lot more aquatic animals than we did in the 1960s. You can see that in this graph. On the x-axis, you have time, and then there are two white axes. On the one side, you have capture versus aquaculture. That's split between blue and red. And then on the other side, you have million tons. Okay. Global consumption of aquatic foods increased at an average annual rate of 3% between 1961 and 2019. A rate almost twice that of annual world population growth for the same period. Okay, this is interesting. It's interesting to calculate annual rates of something. So you can take the average annual rate. It's something you can calculate, and it's an interesting metric for comparing things, for doing kind of studies and checking if there's correlations. Per capita consumption of aquatic animal foods grew by about 1.4% per year. Okay, so the annual world population growth was 1.6%. Okay, and the consumption of aquatic animal foods grew by 1.4% per year from 9 kilos, live weight equivalent, in 1961 to 20.5 kilos in 2019. Preliminary data for 2020 pointed to a slight decline to 20.2 kilos. In the same year, aquaculture accounted for 56% of the amount of aquatic animal food production available for human consumption. So you might think we get most of our fish from the wide open sea. Not the case. 56% comes from aquaculture. During recent decades, per capita consumption of aquatic foods has been influenced most strongly by increased supplies, changing consumer preferences, and advancements in technology and income growth. Okay, so there is more on the market. That's the increased supplies. There's higher production, and so we're like, oh, that looks good. There's a lot more fish in the stores and in the restaurants than there used to be. And changing consumer preferences, we like to eat fish. We want sushi's big now. Sushi. I mean, I didn't have sushi for the first time until I was in my 20s. Now I eat sushi a few times a year. Advancements in technology. That's the aquaculture mostly. The ability to grow those fish, and income growth. We have more money to spend on eating fish. Okay. 4.3.4 Unsustainable harvesting. The increasing global demand for seafood has encouraged use of unsustainable harvesting practices and over-exploitation. Practices include bottom trawling, ghost fishing, and the use of poisons and explosives as destructive methods of harvesting that are unsustainable. You need to know these. You need to be able to list examples of unsustainable harvesting practices. Okay. So bottom trawling. We'll start there. What is bottom trawling? Bottom trawling refers to trawling or dragging a net along the sea floor. So not up in the water, but dragging it along the floor. Benthic trawling is along the seabed, whereas demersal trawling is just above the seabed. Okay, so some are really dragging the nets on the ground in the water, and then some are doing it just above the ground. Bottom trawling accounts for about 30 million tons of fish captured annually, so it's pretty popular. Bottom trawling has now been restricted in certain areas and at certain times because of the damage it does. Bottom trawling contributes to 600 to 1,500 million tons of carbon dioxide annually by disturbing carbon on the sea floor. So when you drag nets through the sea floor, you're putting up massive plumes of dirt. And that dirt is sediment, which, as we know, has captured a lot of carbon dioxide that has settled there. Bottom trawling is also associated with the collapse of various species, including barn door skates, orange roughy, and sharks. Bottom trawling uses a plow-like action in digging up to 15 centimeters of the seabed. Okay, so it really digs in. This creates a cloud of sediment which scares the fish towards the open end of the net. Okay? Regulation of the net size has reduced the mortality of juvenile fish. Okay, so all of this digging and dragging things up in the side, it's not necessarily to catch stuff that's on this on the ground. It's to scare up the fish so that they don't hang out down there and hide, but that they come up and can be caught right into the net. Okay. Bottom trawling operated for over a century in fishing grounds such as the North Sea, it's not far from here, where we are in Sweden, and the Grand Banks. Some areas, such as Venezuela, have now banned bottom trawling, and the USA's West Coast Rockfish Conservation Area limits bottom trawling at depths of 140 to 270 meters to protect the overfished rockfish species. However, as the open ocean is free from national jurisdiction, means there's no country that's regulating it, bottom trawling is unregulated. No laws against it. Ghost fishing. So we just covered bottom trawling. Now let's look at ghost fishing. Ghost fishing, or ghost gear, is the fishing equipment that has been abandoned, lost, or dumped at sea, including nets, long lines, and fish traps. Fish that are caught in this equipment can suffer exhaustion, suffocation, starvation, and finally death. In turn, they attract predators and scavengers that get caught in the same gear. So say you've got a big shipping boat, big old storm comes, the boat sinks, all that gear goes everywhere. They don't go out and get it back. Like, it just pollutes. All that gear is just there. And sometimes they just unload stuff. Like, oh, we don't need this anymore. Boop, over the deck, into the water. An estimated 25,000 nets are abandoned in the North Atlantic every year. I mean, it's thrown away through various means. Each net can weigh over 4,500 kilograms. Ghost fishing can damage sensitive habitats such as coral reefs, enable invasive species to spread, and can devastate shorelines and boats. Due to the durability of modern fishing gear, especially plastic, devastation may continue for decades. So in goat fishing, this is not ghost fishing is not intentional fishing. There's no one out there fishing. It's like the fisherman is a ghost. Okay? The nets are out there catching fish and killing things, but there's no people collecting them. Okay? Submarine drones, remote operated vehicles, can help to remove some of the materials from the seafloor, but the process is dangerous, difficult, expensive, and time consuming. So it's hard to get these nets out of the ocean once they're there. Over 136,000 seals and whales are trapped in lines, nets, and traps every year. That's horrific. Poisons and explosives. So we've covered bottom trawling, ghost fishing, now it's poisons and explosives. Toxins have traditionally been used by some hunter-gatherers to stun fish, paralyze them briefly, so that they can be easily collected by hand. For example, some of California's Native American populations use soaproot species, which contain saponine, as a poison. California buckeye is also used to produce esculin, which is then applied to freshwater pools and small streams to stun fish. Olax is a fish poison used by the Gandhi of India. The leaves of the plant are dried and powdered. When fish are stunned by the poison, they rise to the surface and can be easily collected by hand. Blast fishing or dynamite fishing is an illegal practice that uses explosives to stun or kill large numbers of fish for easy collection. It is widespread in Southeast Asia, coastal Africa, and parts of the Aegean Sea. Underwater shock waves from the explosion stun the fish, which may then rise to the surface. However, the explosions kill large numbers of fish and non-target species, so it kills everything, even the things that we don't want to eat. Only about 20% of the fish killed actually float to the surface. It's not it kills everything, and only 20% floats up to where you can get it. In the Philippines, destructive fishing methods have degraded some 70% of coral reefs and are responsible for reduced fish production of about 175,000 tons. In some places, including Tanzania Tanzania, Indonesia, and the Philippines, sales of ammonium nitrate, that's an explosive, have been restricted or banned, making it more difficult to make explosives. 4.3.5, overexploitation. Okay, we got a little picture here of the Grand Banks area. Overexploitation has led to the collapse of fisheries. So areas where fish are where there's a lot of fish hatching and growing and whatnot, and being, I guess. These stop existing, basically. There have been many fishery collapses, dramatic and lasting decrease in the stocks to a point where the commercial fish can no longer recover. Okay, so the population just crashes. One example happened to the cod fishery of the Grand Banks of Newfoundland, Canada, or Newfoundland. Okay. There used to be a booming cod business there. Cod is a kind of fish, but it collapsed from overfishing. And now we can read this example about it. Overfishing in the Grand Banks of Newfoundland. You need to know an example, so this is good to read. I don't know if it's called Newfoundland or Newfoundland, so just bear with me in my incorrect pronunciation. In 1992, the northern cod population fell to 1% of historical levels due to overfishing. A significant cause of the collapse was the introduction of equipment and technology that increased fish catches. The use of radar and sonar allowed trawlers to track fish. Canadian catches peaked around the late 1970s to early 1980s. Cod were being caught at rates that far exceeded the replenishment of the supplies. So they were being caught faster than they could make new cod babies and grow, right? Grow to adult size. Countries fishing for cod in Newfoundland included France, Germany, Greenland, Portugal, Spain, and the USA. The large volumes of non-commercial fish and bycatch is fish and other things that are ending up in the nets and dying that we don't use, caught by trawlers were not commercially viable, but were environmentally important. For example, capelline were caught as bycatch. As these fish are an important food source for cod, the remaining cod population had a depleted food supply. Okay, so they were trying to catch cod, but they also caught this other species that we didn't want to eat and didn't want to sell. It wasn't worth anything, but it was worth something to the cod because the cod eat it. So that was a problem. In 1968, the cod catch peaked at 810,000 tons, which was around 3 times the maximum yearly catch before the super trawlers. Between 1647 and 1770, around 8 million tons of cod were caught. Factory trawlers took just 15 years to catch a similar amount. Improvements in sonar and radar allowed trawlers to track fish populations, meaning the larger vessels with refrigeration were able to store catches for many months while they remained at sea catching other fish. In 1986, scientists warned that the total amount of cod fishing allowed needed to be reduced by 50%. So there needed to be like a ban on 50% of the cod fishing. By 1992, the cod industry had collapsed, and a moratorium on cod fishing was introduced that year, like a kind of a ban. The cod population had fallen by 99%. So there were only 1% of the cod left from before. Some 37,000 fisherfolk lost their jobs. So that boom in fishing had a really big positive economic short-term benefit for the people with that technology, but the result was 37,000 people lost their jobs. Newfoundland experienced outmigration, people immigrated, and a restructuring of their economy and society. So basically just destroyed their towns, right? Because there was no more work. There was no more cod. In 2000, the World Wildlife Fund for Nature, WWF, placed cod on the endangered list. Global cod catches had fallen by 70% in 30 years. By 2002, despite 10 years of the moratorium, cod numbers were still low. Forage species such as the capelin that used to provide food for cod were now feeding on juvenile cod. Okay, so these species that used to be the food for the cod are now big enough, and their cod are so few that they were eating the baby cods. Although a 2015 report suggested that cod numbers were on the increase, other reports suggested that cod numbers in the North Atlantic would remain low due to global climate change and warming of North Atlantic waters. It is hoped that the cod industry could return to pre-collapse levels by 2030. Maybe.